Factoring the height function gives zeros at 1 second and 5 seconds.
Welcome to Function Marsh. Watch the scene closely first. Here, the shape of the physical environment aligns perfectly with the underlying math. We can read the landscape by looking at the equations carved into the banks and the water lines mapping out relationships. Let's follow a path through the water. This waterway curves along a specific route, mapped out by the standard quadratic function, f of x equals x squared minus 5x plus 6. We rewrite x squared minus 5x plus 6 into factored form, the quantity x minus 2 times x minus 3. Setting each factor equal to 0 shows exactly where our path hits the waterline axis.
The zeros x equals 2 and x equals 3 are x-intercepts, input values where f of x is 0. They are not physical boundaries.
Following a heron further into the marsh, we find a different curve. This waterway dips down into a low path defined by the equation f of x equals x squared minus 6x plus 13. To find the absolute lowest point, complete the square, rewriting the equation into vertex form. F of x equals x minus 3 squared plus 4. This squared part is always 0 or positive, so the minimum value is 4, happening exactly when x equals 3. Rewriting a quadratic into vertex form exposes the absolute lowest or highest physical boundary of a relationship.
Completing the square reveals a maximum height of 4 meters at 3 seconds.
The math targets the extreme value. Now look at a third waterway. G of x equals the quantity x plus 1 squared minus 9. Pause here for a moment. Can you find the axis of symmetry h on your own? Align our function below general vertex form, y equals x minus h squared plus k. To match the required subtraction, we rewrite x plus 1 as x minus negative 1. This confirms h equals negative 1, locating the symmetry line x equals negative 1. Extracting the sign-corrected value of h provides the center line needed to balance a symmetrical environment. We've mapped the specific coordinates of this terrain. This scene shows the features we've uncovered.
Now use one heron flight model from start to finish. The height is h of t equals negative t squared plus 6t minus 5, from 1 through 5 seconds. Factoring gives h of t equals negative the quantity, t minus 1 times t minus 5. The modeled height is 0 at 1 second and 5 seconds, when the heron leaves and returns to the water. Completing the square gives h of t equals negative the quantity, t minus 3 squared plus 4. The vertex is 3, 4, so the maximum height is 4 meters at 3 seconds. The axis of symmetry is the vertical line t equals 3. For example, h of 2 and h of 4 are both 3 meters. Standard, factored, and vertex form describe the same flight, and each form reveals a different feature in context. The heron is 3 meters high at both 2 seconds and 4 seconds.